And by the way, I don't know what it is, if it's like a right brain thing or a left brain thing, but those of you future teachers out there, look at how I always draw my things. I always draw the rope to the left of the worker.
Yeah.
I always do that. I don't know if it's a right brain thing or a left brain thing, but anyway. Let's see. It is 30 feet. So I'm going to put my x equals 0 here. And here's my axis. Here's the x equals 30. And here's my x sub I distance. And what's going to happen at x sub I is I'm going to have a little bit of an increment of rope. Let me kind of make the rope wide for effect there. All right, this rope right here weighs 2.5 pounds per foot. So what does that give me here? I need a delta force. All right, so this needs to be in pounds, right?
2.5.
So I need a pounds per foot times feet. All right, my pounds per foot are the 2.5.
Yep.
And my increment of roadhousing length of delta x. So 2.5 delta x is my work, or my force increment. Okay, and then when I do my work, my delta W, I've got to get foot-pound out of that. So I've got to multiply this 2.5 delta x is being brought up, x sub I feet. So this is going to be x sub I delta F, which is 2.5 x sub I delta x. And that's my work increment. Okay? Okay, now to distinguish between the work done on the rope and the work done on the plaster, all I have to do on the plaster to make it go against the counter of gravity, I just need to make sure that the bucket goes up at a constant acceleration, and that mass, that weight doesn't change, so all I have to do is force times distance on it. I'll treat that separately. If you want to distinguish them, I'm going to say weight on the work on the rope. Right, there's work done on the rope. And I'm going to have the limit as n approaches infinity of the sum from I equals 1 to n of all of these work increments. And I might add, I'm pulling up the rope all the way to the top. So every piece of rope from the piece 0 feet away, that's going to take me a very short time to get it past my hands. It's working leg on the ground, and then gravity just holds on to it. All the way to the very bottom piece of rope. And I guess you might, this is pedantics here, but you might say, well, the bucket could be a foot tall. Aren't we technically pulling from 0 to 29? Let's just assume that the rope goes all the way to 30 feet. So you're pulling every piece of rope from 0 to 30. We're not going to let the height of the bucket affect our answer here. So integral from 0 to 30 of 2.5x dx, that's going to be a quick integral. And then the work done on the bucket is just going to be 30 feet times 16 pounds for 480 foot-pounds. Okay, so the work done on the bucket is simply going to be 16 times 30, which is 480 foot-pounds. And the work done on the rope requires the definite integral. Not a bad one, it's just a one-term integral, and plugging in 30 is going to be the only substantive bound. So let's see. Half of 2.5 is what? Okay, 1.25x squared from 0 to 30. All right, so the only substantive bound is the 30. This would be 1.25 times 30 squared. And what is 1.25 times 30 squared?
1125.
1125 foot-pounds. And so the total work, we take the 1125 plus the 480, and that's gonna give us 1,625 minus 1605 foot-pounds to pull the rope and the bucket.
Yeah, if you think about that, that's a lot.
Well, look at what's bigger. Wouldn't you expect the bucket